Sancho de CoSMoS. Ah, vale. Ah, muy bien, Vladimir. Porque ¿tienes la presentación lista?
Sí, la dejo aquí. Que me acaba de pedir José Ramón que la haga en inglés.
La saga, muy bien,
O sea,
perfecto.
el speech.
Sí, perfecto. Okay, the next lecture is monitoring concrete structure using CoSMoS system.
¿A que se me escucha?
Con este sin enchufas. Aquí.
Well, hi everyone, and welcome to the fantastic world of concrete monitoring. My name is Vladi. I'm the Director of Engineering at CoSMoS Engineering, and today we're going to introduce you to monitoring concrete structures using CoSMoS system. I will go through first a bit of the background for this project and how this background evolves to what is called the maturity method, how CoSMoS implements this maturity method in practice, and at the end we'll end up with a use case analysis of a real project, which is the Benidorm Beach Tower, a project where it has been already implemented, the system of monitoring the structure, and we'll go through the results of it and some interesting conclusions. Okay. So first of all, to put a bit into background, we are in the USA, the 70s, and we have a few accidents, buildings collapsing. Like this example, for example, is the Skyline Plaza collapse in 1973, but also the Pleasance Power Station collapse in 1978, which at the end, after investigations, it was concluded that the structures, within the main reasons for the accidents, the structures, concrete was not mature enough in order to sustain all the loads. So let's say that the temperatures in the site were lower than the ones in the laboratory, and the results from breaking the concrete samples in the laboratory were not realistic of what was happening in the real construction site. So they ended up with a situation where the structure couldn't support the load, and when they started charging it, it collapsed, failed, and there were fatalities. So that was the main reason to start digging into that topic. And almost 10 years later, nearly in 1987, the American Society for Testing and Materials released what is called the maturity method, which is published under the standard ASTM C1074. Okay? Basically, the maturity method, for the ones that don't know it, is a non-destructive concrete testing method, which is used to assess concrete strength. Okay? But concrete strength, the interesting thing about this is, as it is non-destructive, we can do it in the field. We can do it in the real elements. And basically, it relates concrete temperatures during curing with the strength that the concrete is going to have. Okay? So basically, this method is really useful, really easy to, let's say, understand and put into practice. But at the end, when you really want to put it in a project, it becomes quite complicated because you need continuous monitoring for it. You need to start assessing concrete temperatures from the really beginning of the concrete pouring up until the moment you want to assess strength. So in order to manage that volume of data, it has never been put into practice, let's say, commonly. So that's the reason that we decided to develop CoSMoS. CoSMoS, which also stands for Concrete Strength Monitoring System, is a monitoring system that is based on the maturity method and is used to assess real-time and on-site concrete strength. We've used the power of IoT, Internet of Things, and all the new technologies that exist to really get a method from a paper and put it into practice in the field with a huge volume. Now we can process large amounts of data with really simple sensors and transmission device on site, and then start to know the real evolution and the strength of concrete of the monitored elements in the field. It doesn't matter if it's a concrete slab, a column, a pillar, or whatever. Okay? So how does the CoSMoS system work? It's really simple. First of all, we have sensors installed in the structure. We just put some very small sensors, we'll see some pictures later, inside the concrete elements in the rivers. We connect those sensors to transmission devices, and those transmission devices all over the construction site will send the data to a concentrator, and that concentrator will forward the data to the internet, to our servers. In our servers, that data is going to be processed based on the maturity method, on the American standard, the ASTM 1074. Okay? And based on that maturity method, we are going to be assessing concrete strength for any of those elements that are monitored. So in fact, at the end, the user, what they do is they just take their mobile phone, go into the application where they have all the managing of the project and reviewing the measurements, and they can see real time the strength of every element that they are monitoring. So how does that look? The application, basically, people create measurements. The project manager on site or the person in charge of quality control in the construction site, they create measurements, and it's really simple. They just assign two critical parameters to it. One is the physical device that they're going to be using for monitoring. So let's say I get this device and I assign it to this measurement in order to start gathering data. And second, the concrete calibration curve. That's the curve that we get based on the maturity method. Previously to using a concrete mixture, you need to do a laboratory testing in order to obtain the critical parameters that relate temperature evolution with concrete strength. And with those two parameters, they can start the devices and start gathering real-time data. And that data that the application is going to give them is concrete megapascals from the real element on site, nothing related to laboratory. And with those megapascals, they are ready to start working and taking decisions. They know how much resistance or strength the structure needs to acquire. So they are going to be looking into that. And when the applications tell them, they are going to be able to make decisions around it. And basically, that's the information they see. We have here the blue graph is going to be the temperature evolution for a concrete element. And then we have the one in orange, which represents the strength evolution in megapascals. And the calibration on the laboratory is the one that the algorithm takes into account to go from the blue plot to the one in orange and get concrete strength. And that's basically the full scope of the ASTM 1074, of the maturity method. I have a concrete element, I put monitoring of temperature on it, and I start getting concrete strength in megapascals. But we have decided to go one step forward and to assess future predictions, not only real-time estimations, but also future predictions on concrete. We see there the orange graph, the orange part of the curve, is the one as previously, the one that we have for real-time evolution of strength. But using data science and some algorithms that we've developed, we start assessing until the full 28 days cycle of concrete curing, the future strength, the estimation of future strength. And that really makes CoSMoS a very attractive tool for project planning, because you don't only know what's happening on the real element, but you can start assessing when to plan next stages of your building and when to prepare your materials and optimizing next concrete pourings. So at the end, with all of this information, what do we have? Well, in first place, an increase in labor risk prevention, in what is called in Spain PRL. Okay, and that was the reason why the ASTM 1074 was released, because of those accidents and collapses in the past, to avoid that happening again. But then let's say that in project managing, it has really a lot of benefits. First, the quality control previous to the execution of the project, because that's usually not done for normal concrete mixtures, but if you are using CoSMoS, you are forced to do this pre-calibration of the concrete mixture. So you start already seeing things that you don't like in concrete, behaviors that you don't like, and maybe you want a concrete that strengthens faster on the early stage of curing, and it's not like that. So you have that information. But also because of determining in real time the acquired strength, we have a lot of extra information to improve project management, and we have demonstrated, we'll see it afterwards in the numbers, that you can cut construction times from the structure in up to 20%, depending on weather conditions and temperature conditions on site, but those numbers can be achieved. And that obviously has a reduction in the indirect costs of the building, because we're going to have, if we shorten up the time of the project, we are going to be saving money. And then, a bit apart, we also have this tool, we're integrating the tool with the BIM methodology, and the data that it provides is a source of information for the 4th, 5th, and 6th dimension. And as well, in collaboration with the University of Malta, we have developed an LCA, which is a life cycle assessment of the product. And because of the optimization in construction times, we're also noticing a reduction in the carbon footprint of construction projects of up to 50 kilograms of CO2 equivalent per concrete cubic meter poured. Okay. So to put it into practice, what do we need to do in the field? First of all, as I said, do the calibration in laboratory. We'll have, based on the ASTM 1074, we have a method to prepare some concrete samples, put them in laboratory, monitor them, and start breaking them and assessing their strength in different ages. And with those concrete samples and the temperature data that we gather out of it, we will be able to calculate the critical parameters for that mixture and the ones that will relate temperature evolution with concrete strength. Once we have that calibration curve, we are ready to start installing sensors in the field. And to do so is really simple. Installation of the sensors in the field takes just a couple of minutes. First of all, the sensor, which is the thing that gathers data, the temperature data. It's installed in the rebar of the elements. It doesn't matter if it's a slab or a vertical element or whatever, you just install it in the rebar. There are recommendations on the locations to install them and as well on the number of sensors to install in a structure. And those recommendations are based on the ACI, which is from the American Concrete Institute, standard 228. And that standard gives recommendations and guidelines for many non-destructive methods for testing concrete. And the maturity method is one of them, and establishes preferred locations for the sensors, positions in the structure, and so on. Once we have the sensor located in there, we just cable it out of the formwork, so we are able to install the monitoring device, the data transmission device. So the data transmission device, which we call the CTM, the CoSMoS transmission module, is the thing that you connect the sensor to and start sending the data out to the internet. This transmission device is installed out of the formwork, so inside concrete we only have that small sensor. And as well, location for it depends a bit on the concrete element that we are monitoring, but usually it's a location where it does not interfere with other tasks that are going to be performed, and can be left there for at least between 4 to 14 days, depending on how long you want to monitor for. So knowing how to install everything, here's a bit of a diagram, of an overview on how the whole system looks like. We can see inside the elements in the rebars, the sensor installed, that it's cabled out of concrete, and then we install the transmission device. At the end in the structure, the transmission device, you reuse it every time because you can take it out and connect it to a new measurement once your measurement is finished. And the only thing that is to concrete is the sensor with the cable that you just cut it off and it's left there forever. Now we're also starting to assess new methods of using those sensors in order to assess afterwards when the structure is finished as well thermal runaways on the building and so on for energy efficiency, because you already have temperature sensors installed all over your building. So with all of this information and that now that we know how the system works, I'm going to introduce you to the real use case that we've been running for 14 months now, the Benidorm Beach Tower. Benidorm Beach Tower is a 36-floor skyscraper in Benidorm, Alicante, developed by Ali Building and built by ECISA, both Spanish companies. And CoSMoS on it has been part, since the beginning, of the quality control plan of the building. Okay? There have been more than 20,000 cubic meters of concrete poured, more than 5 concrete mixtures, and overall, we have put measurements and sensors in 681 locations, giving us a total of more than 670,000 data points of temperature, concrete strength, maturity, and so on to assess and process. And with this data, a comparative study has been made, comparing the results of CoSMoS versus the one of the Spanish legislation for structural concrete, which is the EHA, and also versus lab results, which were the method they use in the building site in order to decide the go or no go for next stages. So, based on this data, what's the first thing that we need to assess? That is what usually people don't take into account. That a same concrete mixture in different location means that the concrete is going to be curing at different conditions. And that equals to different age of concrete, because age is not time. Age is the combination of time plus temperatures over time. And thus is going to be different strength. And that can be really seen in the plot that we have. We see there the same concrete mixture. First, the green curve that we see in the middle is the one from the laboratory. We have the first day, the concrete pouring there, and we move it to the laboratory in a constant temperature near 20 degrees in the chamber. But then we see the same mixture in summer at the top, and in winter, which is the blue curve. And it's clearly seen here that versus the laboratory results of the one that is in the laboratory, results of strength of the monitored samples and elements that are on construction site, if they're in summer, they have a greater strength at the same time, at 7 days, because they have cure at different conditions and they have age faster. But and that would mean that we would be losing time if we are just looking into the laboratory results. But at the same time, we see here that even though it's in Benidorm, in Alicante, very nice weather, even in winter, there are moments that your concrete element in the construction site in winter does not reach lab specifications at the same time. And that was the critical issue that led to the development and the publishment of the ASTM 1074. Those collapses, the collapses that were caused because the concrete in the construction site was not mature enough compared to the one in the laboratory, and people was looking at laboratory results to decide for the go or no go. So knowing that already, we will see a summary of the results for horizontal elements. The average time to reach concrete specifications with CoSMoS was established after the whole monitoring between November of 2020 and February of 2022 at 5.6 days. A bit more over 7 during winter and a bit less of 4 during summertime. At the same time, if we compare it to the legislation, the EHE, we see that in average, they account for a period of 10 days for the shores and formwork removal, which is 7 days for summer months and 13 days for winter months based on temperature conditions on site, which is already quite a difference. And that would mean that we were losing efficiency in the construction. But if we also check for the method they use in the construction site, laboratory testing of the concrete samples, they were breaking them in a fixed time, always at 7 days. So that would mean that in many times, some months in winter not, as we've seen in the blue curve, but a lot of months during summer and the rest of the year, would be able to even shorten construction times. And that we can see it clearly in the plot, where we relate average site temperatures, which is the blue curve, with the strength that concrete acquires over the period of time. And you can see the intrinsic relationship between them. So that demonstrates that concrete age is not only related to time, but also to temperature evolution over time. And a bit more of a summary here of the results of the horizontal elements. We clearly see the example that I was mentioning when in certain months, because of temperatures on site, concrete was not mature enough compared to laboratory. In this case, the difference was not huge. Probably it wouldn't affect anything. But in some colder climates, that can be an issue, and that can lead that if you expect your concrete to be in 30 megapascals, as the laboratory says, and you are really in 20 because it has not properly cured, and you overload the structure, or you attach the crane to it, like happened in the collapses in the USA, you may have some issues in the structure. But overall, from the project, according to the results we have, a total of near 3 months, 84 days, could have been saved on the structure with proper planning, accounting not with the Spanish legislation, which is more conservative, but with the time they were already doing things in construction site, which was always 7 days. And what about vertical elements? Well, we have a similar thing. Summary for vertical elements, at the end, we see that there's a huge difference between winter time and summertime, also known as weather conditions on site. That is greater in the early stage that concrete is. That difference is even greater. We have, for example, to reach 44% of the characteristic strength of concrete at 12 hours. The difference between summer and winter time was near 30% of strength. And that not so visible in the plot, but if we check on the table in the numbers, you see as well that the color code is completely related on the difference of strengths. So what can we conclude out of it? That concrete curing is a physical process, okay? It's quantitative because it's a number. It's a physical process, a number. We want to assess strength, which they are giving us in megapascals or whatever. And depends on temperature over time, not only time. And needs to be known because in construction, you need to do tasks based on when your concrete has enough strength to sustain those tasks. So we have many methods to assess it. Usually we have the legislation and it tells you some numbers. It's based on ideal scenarios. It tells you a number of days in order to remove your formwork completely or deshore the structure. But it's qualitative. It's just number of days, okay? Based on average temperatures on site. So it's not giving us real useful information. The other common thing that always has been done is the laboratory testing, which this one is giving us more real information. It's already a quantitative testing. We are assessing a real parameter. We are testing for a physical variable, which is concrete strength. The only thing with this is that is not related to the real concrete being poured on site. It's the same concrete mixture because you take the concrete samples out of the same truck in the building site before pouring, but they are not curing at different conditions. And we've seen in the plots that then concrete will end up with different strength over the same period of time. So here is where CoSMoS comes in. It reads for physical variables, so it's also a quantitative method. And because of the use of the maturity method, it correlates them to a strength, but a strength of the real element on site with the real temperatures that is curing. It doesn't matter that it's freezing outside or that we are at 40 degrees outside. It will not be like the concrete samples in the laboratory chilling at 20 degrees. Okay? So that's basically what we see. And what are the specific conclusions for the project of Benidorm? Well, first, that CoSMoS clearly covers the gap between the information missing from the laboratory testing up until the real conditions of concrete on site. Okay? It has been demonstrated the relationship that concrete age also depends on temperature and then seasonality. And there's a huge difference when building in winter and when building in summer. And those are things that should also be considered in project planning on the first stage. Usually calendars are made the same for the whole year, and those differences should be taken into account because we've seen that sometimes there's even a 30% of difference. That in good weather conditions, a structure could be built much faster. And not only faster because of doing things before without considering if your structure is strong enough or not. It's faster by respecting the same specifications that you need to reach. But also, even here in this project, that weather conditions were good in winter, there were moments that the structure was not strong enough. So we had these issues that could lead to the accidents as we saw in the introduction, accidents that happened in the past and that are still happening. There are studies from UPB that I can share with you that have assessed accidents in construction, and in the very recent years, there's a few percentage of them which is caused by a non-strong enough concrete. Okay? But overall, for the Benidorm Beach Tower with CoSMoS, with proper project planning on top of it, they could have saved 84 days of the structure time. And that also, based on the LCA, would have been translated in over the 20,000 cubic meters of concrete that were poured in a reduction of carbon footprint of nearly 50 kilograms of CO2 equivalent per each of those concrete cubic meters, which is a lot. And well, we are still processing data. There's a lot of data to process, the more than 670,000 data points that I mentioned, and we're still discovering new things. For example, how the shades affect the project times, and how different concrete elements, if I have a column and I put a slab on top of it, how thermal transmission between the two of them, as one is curing and the other one is not already, also happens. So there are a lot of interesting things in that field that we are still researching, and we plan to be publishing more information in the future. So that has been all. Thank you for your attention, and you can reach to me or check on the website to get more information on it.
Thank you. Does anyone have a question for him?
Puede ser en castellano también.
Yes, I have a question. As your presentation has shown, as the sensors should be placed on where the American regulation say or suggest, but I think it's for isolated elements, beams, pillars, columns, and so on. And one thing I have found from my research, particularly, is have you ever compared results coming from sensors from the same mathematical model coming from, for example, a finite element method or analysis? Because the thing I have found is the stress within the mass of concrete depends on a specific position of the sensor. So there's a lot of research there, like, for example, Stratton time method and so on. So it depends on the precise position of the sensor. So even to being paired with the bars or not, because the comparison made on the laboratory is just isolated within a test. So does it affect the results, or have you compared the mathematical model and mathematical model coming from finite element method with the results coming from sensors?
So from finite element methods, we haven't compared anything. What we've done is, instead of doing only laboratory testing, put also concrete samples next to the monitor element for them to are in the for them to be in the same curing conditions. Okay. In terms of the location of the sensors that you mentioned, we are based on the standard recommendations, which is backed up by those kinds of studies that you mentioned. And for example, this kind of things is that in vertical elements, if you put the sensor on the very bottom of the element, you're going to have fake results because it's going to be really hot and it's going to tell you that your concrete is cured in a few seconds, let's say. But the same thing happens if you put it at the very top of the element, that you're going to be really affected by external
Depending
conditions.
on the element connected or not, slab, for example, connected with a wall, concrete wall,
Yeah.
so nearby there, or the connection there, so it could be affected with both elements.
What I was mentioning here in the conclusions with the things we were discovering between the heat transfer between different pools of concrete. We have noticed that if you have recently concreted a column and you put the slab on top of it after 2 days, the column is starting to lose temperature, like let's say the big part of the chemical reaction over the first 2 days. And then because of putting the slab on top of it, you are not only curing the slab, but also providing extra heat to the column. Yeah. So those are the things now that we are trying to model with this all the data points we have. Because if you really plan not only isolated stages, but the combination of them, you could be having your concrete curing instead for, like strongly curing instead of only for 2-3 days to extend that time of internal temperature of concrete and the strong reaction for near 1 week.
Okay. Any other question?
Voy a decirlo en castellano
Sí.
porque si no se me haría imposible. Creo que has estado hablando sobre, ha habido un momento que has estado hablando sobre el porcentaje de variación que había entre los resultados que obtenías con este tipo de test y los que se obtenían en el laboratorio. Me gustaría saber si existe una diferencia de error mayor o menor dependiendo de la temperatura en la que se fragua el hormigón.
No hemos visto diferencias, ¿vale? Sí que se ha notado porque cuando se hace la calibración al final es un modelo matemático. Depende mucho de cómo se hace la calibración de bien, hay un margen de error, que normalmente está en torno al 10%. Entonces, cuando la aplicación dice que está en 30 megapascales, sabes que normalmente puede estar en más o menos un 10%. Depende también en qué momento, porque si es cercano a los 28 días suele ser más exacto. Cuando hay más incertidumbre es en el primero y a veces en algunos a la mitad, depende qué tipo de aditivos lleve el hormigón. Vale.
Ok, gracias.